All right, this is, if this is working, this is Dr. Smith, and I am going to go through an example of a resistor capacitor circuit, better known as an RC circuit, to sort of illustrate some of the principles involved, what exactly is going on here, the kinds of questions you might see on the AP exam, and just to sort of generally give you an idea how we go about this stuff. Okay, so I've got this problem here. I've got obviously I drew this diagram by hand. Took an incredible amount of time. Anyway. So the problem explains what's going on. You've got this circuit where you have a power supply, you have a switch, and you have a resistor and then a capacitor all in series. So when the switch is open, of course there's no current flowing because you can't have current flowing through an open switch. So we have I equals 0, and we're going to say initially with the switch open, the capacitor is uncharged. Okay, and then it's closed at, right here as it says, at time t equals 0, and you get this happening. Okay, what's going to happen here, even though they don't show it in the diagram, is that the current is going to vary with time, and so is the charge. It's going to be a function of t. Okay, so what you have to do to sort of fully solve this and understand it is solve a differential equation. Now, typically, what the AP exam will ask these days, I can't promise, of course, but typically what the AP exam will ask these things is they will ask the first three. So they will ask you to write the differential equation, but not solve it, and they will often ask you to write it and never solve it. Okay, and then they'll ask you to evaluate what happens sort of at the very beginning of the system, right after the switch is closed, so just after t equals 0, and they'll want you to know the charge on the capacitor after the switch has been closed for a long time. And they might also want you to know, or they'll ask you something about the state of the system after a long time. And they might also want to ask, ask you to draw a little plot of what happens. Okay, so I may just stick that one in. D is probably not on the AP exam. They'll probably won't have you actually solve it, but I'm going to show you how to do that. It's not terribly hard once you have these guys, but it does take a little extra thought. Okay, so for part A, the thing we do here is we have a loop circuit. We have no branches, so we only have to worry about, really, this is after it's turned on, so maybe this is what we've got going on. The purple current goes that way. It doesn't matter if you don't know which direction the current goes. Pick one, and then if you get a negative answer for current, then you picked wrong. And you just, that just means your current goes the other way, but your solution will still work, okay? Similarly, you can pick a charge for the capacitor or a polarity for the capacitor. That is, which side is going to be positive, which side is going to be negative. It makes sense to pick it so that positive current flowing in, that means positive charge flowing in here, will give you a positive capacitor charge there. So, it's easier to pick it so that your current and your charge at least match up. Okay, so what we do is we apply Kirchhoff's voltage law, okay, just like we do with any single loop circuit. And Kirchhoff's voltage law says the sum of all delta V's around a circuit, by which I mean change in voltage, not change in velocity, is 0. Okay, so what I'm going to do now is I'm going to find the voltage difference from C to A. So I'm just going to pick this as my starting point here. Okay, this is where I'm going to start my Kirchhoff's voltage law loop. And I'm going to arbitrarily define this. I could arbitrarily define this as 0 voltage. I don't need to in this case, but I could, okay? In fact, I can just write in V equals 0 there, okay? So 0 voltage all along here. The switch acts like a closed wire. We're assuming, as always, ideal wires, so there's no need to worry about resistance in the wire. Still 0 voltage here, and then we cross this ideal power supply or ideal battery. And that means our voltage goes up by some EMF, which is, that curly E. So our delta V, actually, I'm going to go delta V as we go from C to, well, little c to little c. I'm just going to say this is delta V all around the circuit. In fact, I'm going to draw below it a little arrow circling out itself. Okay, and then I'm going to put in, here's the voltage change we just found, getting from C to this side, and that'll carry us around to A, because again, no voltage change there, okay? So the EMF gets us from point C to point A, Okay, and I'm just scribbling this in below to sort of give us an idea where we're going. Okay, now you're at point A. Now we're crossing this resistor. The current goes this way, okay, across the resistor, and that means the voltage has to be lower at B than at A. You have to have a higher voltage. If you have current through a resistor, it has to be going from the higher voltage to the lower voltage, which means the change in voltage as we cross the resistor will be negative, and it will be, by Ohm's law, it'll be IR. So we're going to have I, and I'm going to go ahead and make I a function of time, okay, because, in fact, it is a function of time, okay, and then just the resistance there, okay, so that gets us from A to B, and then finally, we have to go from B to C across the capacitor. So what's the voltage gap across the capacitor, or the voltage difference across the capacitor? Well, that's given by the capacitor formula, which is Q equals CV. I'm going to write that over here, okay? So Q equals CV for a capacitor, okay? And then let's remember what our sign is here. Well, first of all, so we want to find the voltage change, so that's going to be V equals Q over C. And we've got a positive charge here on this left plate and a negative charge on the right plate, which means the voltage at B will be higher than the voltage at C. So we're going to subtract Q, which is a function of time, over C. And that's going to be our delta V. So that gets us from point B back to point C. Okay. So now we've gone from point C to point A to point B. These are using the little lowercase letters down here. And then point B to point C. That gets us all the way around the loop, back to C, and that means the total voltage change by Kirchhoff's voltage law must be 0. Okay? So all we need to do now is turn this into an actual differential equation. I'm going to, no, I'm not. Okay, so, yeah, I thought I had an eraser. I probably do, but I don't know where to find it. Okay. So anyway, what we're going to do now is we have to get these into sort of a single function form, so a single unknown. We have right now two unknowns. We have this current as a function of time in this equation, and we have Q as a function of time, charge as a function of time. So the relationship is, and if you think through what's happening here, there's charge accumulating on this plate of the capacitor, positive charge, and there's negative charge being left on this plate of the capacitor. Okay, and this current here is the rate at which charge is flowing around the circuit from this side of the capacitor to this side. So what's going to happen here, what's going to, you know, what we're going to use here is that current as a function of time is the rate of change of the charge with time. Okay, so this, as this charge accumulates here, the rate at which it's increasing is in fact equal to the current, which is I. Okay, when you, and it's common, by the way, when you're taking the derivative of something with respect to t, you assume, if you're going to write a differential equation with this, it's assumed when you write something like this that q is in fact a function of t. Okay, so the reader would assume that if you're going to use dq dt in your equation, which we're about to, that you know that q is a function of t, because if it weren't a function of t, then that would be 0, right? And then you wouldn't write it at all. Okay, so the differential equation then that we get to is going to be, I'm going to write it here first as EMF minus, and I'll put R dq dt, okay, minus, and I'm going to, just to sort of make things a little nicer looking, I'm going to write 1 over c times q of t, okay, equals 0. This here is a good enough answer for A. You don't need to simplify any further. This is a differential equation in Q of t, and that is all you would need for part A on the AP exam. Now, I would say I probably like to simplify it a little further and get us to something like, I'll tell you what I'm going to do is I'm going to move the EMF over to the right side, okay, and I'm going to make it, I'm going to keep it positive. So what I've got going here is a sign flip, and I'm going to go, and then I'm also going to divide by R. You know what? I'm just going to write it out, okay? dq dt, okay, and then plus 1 over RC times Q as a function of t equals EMF divided by R. And I think I've got that right. Yes, I do. Okay, so let me just move this because I'm so picky about these things. I don't know why. Okay, so yes, go away. All right, perfect. Okay, so this is our differential equation in a slightly more compact form. This is more normal for solving differential equations, but you don't have to get there, at least not initially. I like to do this because it makes things a little easier to see, but that's something, you know, that you can learn to do yourself if you want to. It's something that comes with experience, knowing when to do it, whether to do it's a good idea. So for part B, for the AP-ish question, we have to find the current through the resistor immediately after the switch is closed. So B, we want to find I at time t equals 0. Okay, so what else do we know about this circuit at t equals 0? Well, we know the initial charge of the capacitor is 0, so let's say Q equals 0 at t equals 0, and that means then I'm going to plug those into our differential equation here, and I'm going to get out EMF minus R times, and remember dq dt, it almost might be easier to use this one, but I'm going to just go here. dq dt at that time is our current at that time, so this is our current at time t equals 0, which I'm going to call I0 just for, you know, I at time t equals 0, okay? And then minus 1 over c times q of t. Q of t at time 0 is 0. So this whole term is 0. And in fact, I didn't even need to write the negative sign, so I'm going to save it by making it part of an equal sign. And then what you get is your initial current, and I'm writing it as I naught. You wouldn't have to. By some simple, you know, substitutions is the EMF of the battery divided by R. And that's your answer to part B. Helpful thing to note here is that this is also the current you would get if there were no capacitor. And what this tells you is that a capacitor that's uncharged behaves like a short circuit or like just a wire going through there. Initially, it is very easy. Oh, I'm sorry. I'm going to have to pause this right now. And